Thank you everyone for making it to the final lecture in the Deep Reinforcement Learning series. Today we're doing something a little bit different from the sort of technical content of previous weeks, and we're covering goal misgeneralization and reward hacking. So the theme of today's lecture is failure modes in deep reinforcement learning. I'm going to sort of explore these different ways in which deep reinforcement learning algorithms can fail. So we're going to cover these two failure modes, and that's sort of what we're going to do today. So it's very simple structure for today's lecture. We're going to start by going through what goal misgeneralization is. And once I've explained the basic idea, we're going to cover examples of goal misgeneralization. And then following that, an explanation for why goal misgeneralization occurs. So we're going to go into the details of what mechanisms make this happen, what it is about, what it isn't about, and stuff like that. Then we're going to cover reward hacking. And we're going to cover two specific situations in which we might see reward hacking, which are reward shaping and reward models. Okay. Before I begin, I'll just say that these are two distinct failure modes. They have a relationship to one another, but they're very different, and you can have one without the other. They don't come along with one another. They're sort of distinct ways in which deep reinforcement learning can go wrong. All right, let's jump right in. So we'll start by talking about goal misgeneralization. So when we train a agent through deep reinforcement learning, regardless of the method that we get, we often see goal-directed behavior displayed by that agent. And we can distinguish between two different types of goals. We can distinguish between the goals that are encoded by the reward function. So when we set up our reinforcement learning agent and trained it with an algorithm, we used a reward function, and that reward function encodes some goals that we want our agent to learn, that we're looking for our agent to pursue. And we can distinguish between that set of goals, the ones encoded by a reward function, and the goals that the learned policy appears to pursue, or internally is trying to pursue, right? So these are two different things, and they don't necessarily have to be the same as one another. Goal misgeneralization occurs when you have a learned goal, so the goal that the policy has learned to pursue is distinct from the goal encoded by the reward function. So it refers to this separation, this coming apart of these two different sets of goals, the goal that's encoded by the reward function and the goal that's learned by the policy. Yeah?
So when you say encoded, do you mean the literal values of the reward function, or do you mean what the designers intended when they were writing the reward function?
So when I say encoded here, I am talking about what the reward function actually encodes, not what the designers are getting at. And so when we come on to reward hacking, we'll talk about discrepancies between what the designers intend and what the reward function encodes. But for goal misgeneralization, we're going to assume that the reward function actually encodes the behavior that you want, right? So there's nothing wrong with our reward function in the goal misgeneralization setup. Okay. So goal misgeneralization, as I said, refers to a situation in which these two things come apart, where you can have the goals that are encoded by the reward function come apart from the goals that are learned by the agent. When does this tend to happen? So goal misgeneralization is often seen when you have a distributional shift between the training environments and the testing environments, or the deployment environments. Right? So you have some set of environments that you are training your reinforcement learning agent on. So you're training your policy on. And you have a different collection of environments that you're actually going to deploy the agent in. So a good example of this might be if I'm trying to train a self-driving car, and the way I gather data to train it is just by going to like an empty parking lot and getting it to drive around this empty parking lot and avoid the obstacles there, right? And then if I then take that and deploy it in the real world, there's going to be a massive distributional shift between the kinds of things that it sees when it's in training, just driving around this empty parking lot, and the kinds of things it sees when it's in the real world, right? Because in the empty parking lot, there aren't pedestrians, there aren't weather hazards, there aren't other cars, right? And so there's going to be a big discrepancy between my training distribution and my testing or deployment distribution. And so goal misgeneralization often occurs when we have this distributional shift between these two sets of environments. And we get goal misgeneralization when we have a distributional shift if the learned goal does well according to the reward function in the training environments, but not in the deployment environments. So we specifically care about it when our reinforcement learning agent has learned a goal, has learned to pursue a certain objective, and that objective does well according to the reward in training, but poorly according to the reward in deployment, right? So we'll go through some examples so you can see what I mean by this and how this can happen. So yeah, let's just go through a few examples of this kind of situation. So the first example is Coin Run. This is like the most popular example of goal misgeneralization. So Coin Run is a platformer video game consisting of a procedurally generated set of platformers. So a platform game is a 2D game where you just run across the screen and you can jump over obstacles and often like interact with various elements, and there might be enemies that you have to jump and dodge over, stuff like that. In Coin Run, you have to navigate through this 2D environment until you collect a coin. So that's sort of the aim of the game. And indeed, our reward function is just going to be 0 everywhere and then +1 for getting a coin. So you reward the agent with a reward of +1 when it collects the coin. Okay, it's important to specify here that this reward function, there's nothing wrong with it, right? It's not misspecified. It's not encoding something we didn't intend it to encode. We want an agent that learns to collect the coin, and so we will reward the agent if and only if it collects the coin, right? There's nothing faulty about the way that we've set up our reward function. So now we have to come to the distributional shift. What's going to be different between the training and the test distributions? So in training, the coin is always going to be located at the far right end of the environment. So the agent will run across the environment, and at the very end of the environment, there's a coin, and it has to just go and get that. And this is very similar to Mario, say, where you're always going from left to right across the level, or usually anyway. But then in deployment or testing, the coin will be randomly placed throughout the level. So we have this distributional shift where in training, the coin is always in one place, and in testing, the coin varies its location throughout the level. All right. So now let's have a look at the agents in the training environments. So hopefully this works. So as you can see, it's a nice little platform game. There's like a spinning thing that it has to avoid, and it just runs across until it gets the coin. All right. Yep, there we go. And we'll see another example. And as you can see, the agent is very competent in these environments. It can jump to avoid enemies. It can jump over pits. And yeah, it can go until it reaches the coin. Right? So if you just look at this agent during training, it appears like the agent has learned the correct goal. It's learned the goal of go to the coin, right? Which is what the reward function is encoding. It's encoding get +1 if you get a coin and 0 everywhere else. But now let's have a look at what happens during testing. So we'll set him off again. Okay, there's the coin. And he just runs straight past it and goes straight to the end of the level. And then he's really confused because by now the level is usually ended, but it hasn't for some reason. All right, let's see another example. The coin's right there, jumps over it, and then keeps going all the way to the end of the level. Yeah. All right. So this is an example of a distributional shift where the training and test distributions have different properties in their environments. And we see that the agent has not learned a policy that does well outside of the training environment. So in the testing environments, these policies aren't doing well anymore. Let's cover another example. So maze is sort of a similar example. So the maze environment is a 2D procedurally generated set of mazes. And the player, represented by a little mouse, has to run through the maze and obtain cheese. So there's cheese somewhere in the maze. The player has to run through and get the cheese. And during training, the cheese is always located in the top right hand of the maze, right? And we're going to reward the agent with a reward of +1 when it gets the cheese and 0 everywhere else. So again, I have to specify there's nothing wrong with the way that we set up our reward function. It's not that we've set up our reward function in some faulty way. Our reward function is perfectly encoding the goal that we actually want the agent to pursue, which is to get the cheese. And then, as before, during testing, we're now going to randomly vary the location of the cheese. So we're going to randomly place it throughout the maze, as opposed to always placing it in the top right-hand corner. All right, so I'm sure you can probably predict what's going to happen now. And I won't show you the testing clips, or just have a look at the test environments. Sorry, the training clips, just have a look at the test environment. So we can see that that's where the cheese is. And so if the agent had correctly learned the goal of go to the cheese, it could just simply run up here and get it. But I think you can probably imagine what's going to happen when I let the agent go. It just goes straight up to the top right-hand corner and just stays there. And another example here, and again, just runs straight up to the right-hand corner, completely ignores the cheese. Right? So in both these examples, the goal of the agent has again misgeneralized, right? So the goal that we wished it to learn was go and get the cheese, and the goal that it actually learned was go to the top right-hand corner. Right? So now we'll cover, does anyone have any questions before we continue? Yeah?
Probably in the explanation part, I don't know. But the problem basically is the true reward functions are specified because there are multiple reward functions that align with the training data, and then kind of the model chooses the one that's most aligned with its inductive bias. And yeah, I guess the solution is to create more various data such that there's reward functions align with the training data.
Yeah, that's exactly right. So we'll go into the details of the explanation now, but the basic problem is that there are multiple sets of goals that all result in good behavior in the training distribution. So in the coin run example, the goal of get the coin and the goal of go to the right-hand side of the map both do well according to the reward function. But the goal of go to the right-hand side of the map is in some sense simpler or easier to learn for the agent, and so it will naturally learn that goal as opposed to the goal of go and get the coin. And in the maze example, the goal of go to the top right-hand corner is easier to learn in some sense than the goal of get the cheese. And because it does equally well under the reward function, there's no reason why it shouldn't be learned. Now let's sort of unpack those concepts a little bit. So here's things that aren't true of goal misgeneralization. So first of all, is the problem that the policy is bad, that the agent just hasn't learned well, that we've done a poor job of training our agent. So could it be an indication that our policy is bad and we either need a different learning algorithm, or we just need to train for longer, or some other hyperparameter needs to be varied, we need a bigger network or a lower learning rate, whatever. And no, it's not that the policy is just straight bad. And two reasons why it's not this. So it's typically very good at pursuing the goal that it has learned. So a feature of goal misgeneralization is that the agent very competently pursues the goal that it has misgeneralized to. So it very competently runs to the far side of the map or goes to the top left-hand corner of the maze. It has no trouble pursuing the goal that it has misgeneralized to learn. And also, on the training distribution of environments, the policy obtains a very high reward, right? So in the training distribution, there's nothing wrong with the policy. The policy is doing great. It always gets the coin. It always gets the cheese. And if you train for longer, you won't alleviate the problem. Right? Is it an issue to the reward function? I've already sort of discussed this a couple of times. And could it be that you haven't specified the reward function correctly? And no, it's also not a problem with that. So goal misgeneralization is not to do with incorrectly specified rewards. It's to do with the environment distribution. So it's to do with the distribution of things that the agent sees in training and in deployment. It's not to do with the nature of the reward function that we're using to train the agent. All right. So to unpack the things that we just mentioned about how this happens and why it happens, I'm going to speak briefly about how rewards work in reinforcement learning, or how the correct way to conceptualize their operation is. So a very standard way to understand what the reward function does in reinforcement learning is that rewards are the thing that the reinforcement learning agent is trying to maximize. So we're training an agent, and the agent is in some sense trying to maximize reward. but I'm going to claim that this is actually a really poor way of understanding how rewards work and what their purpose is within RL. Instead, the correct way to think about rewards is as a selection mechanism. So the idea is that inside the neural network that we're training, there are multiple, what I'm going to call cognitive patterns for different kinds of behaviors. And rewards are the mechanism by which we choose different cognitive patterns to sort of reinforce within the agent. So we strengthen some patterns and weaken others, and the mechanism of selection of patterns is the rewards that the agent is receiving. So let's sort of unpack this a little bit, go into some more detail. So the reinforcement learning agents, one reason they don't maximize reward is that they never see it, right? So to go into some detail here, for an action value method, so this is a method like DQN, you're taking in, you have a neural network that's taking in state action pairs and computing their values, right? And this neural network that's taking in these state action pairs, it never gets the rewards, right? The rewards don't get fed into that network. Instead, the rewards are used to construct regression targets that are then used to train that network, right? So in other words, the purpose that reward serves is to push up the values of certain state action pairs, right? So it's used to select for certain cognitive patterns within that Q function that assign high value to certain state action pairs and low value to other state action pairs. It's used in this selection way. The same is true of policy gradient methods. So in a policy gradient method, again, you're just feeding in the states, right? You're not actually feeding in the reward to that policy that you're learning. And so the way the reward works within the algorithm is to get the policy to fit or unfit from certain actions in certain states. So to encourage it to take certain actions in certain states, or discourage it from taking other actions in other states, right? And so the reinforcement learning agent isn't seeing the reward. Instead, the rewards are used to determine which patterns of behavior, or what I call internal cognitive patterns, to strengthen or weaken within the system, right? And that's what the rewards are doing. And so under this lens, seeing them as a function for selecting different cognitive patterns, there's no reason why training a reinforcement learning agent must cause it to, in some sense, internalize the reward function. So internalize the goals that are encoded by the reward function. So the sort of developmental perspective on goal misgeneralization, how does this happen? What leads to it happening? Well, during training, at the start of training, some cognitive pattern develops, which is the misgeneralized goal, and this cognitive pattern encourages the agent to pursue the misgeneralized goal. So either in an action value method, it's assigning high values to misgeneralized goal states, or it's assigning high probability to actions that pursue the misgeneralized goal, right? So some internal cognitive pattern that's that sort of represents the misgeneralized goal. And because the misgeneralized goal does not cause sort of bad behavior, or does not do badly according to the reward in the training environments, these cognitive patterns get reinforced during the training process. So these patterns result in high rewards because in the training distribution, it's very hard to see the difference between the misgeneralized goal and the true goal. And so because of that, these patterns get selected for by the reward function. So by our training algorithm, we select these cognitive patterns and they become more prevalent in the agent, and eventually they become sort of dominant. And because there's no selection mechanism against them, there's no way to weed them out during training, because in the training distribution, they do really, really well. I think that's yeah. Does anyone have any questions before we go on? Yep.
So if it's not truly, well, whatever truly means, trying to pursue a goal, sort of internalize a reward function, is the word agent a misnomer?
Yeah, so the question was about the use of the term agent, and in reinforcement learning, we use the term agent to just describe like the reinforcement learning system as it interacts with the environment. So it's a technical term, and yeah, it's not meant to denote anything about sort of the metaphysical status of these things. So it's not meant to imply that they have like cognitive faculties or whatever. They're just neural networks, but the term we use to describe them is a reinforcement learning agent. But in the case of Goleman's generalization, it is like correct, I think, to think of them as having a goal of some kind. Yeah. Yeah.
Are we at the end of the Goleman's generalization part?
One more slide, and then yes.
Because my like bigger question is basically what makes Goleman's generalization or target misgeneralization in reinforcement learning different from supervised learning? Because if I have like a dog classifier and I classify huskies, and my classifier basically just learns no means husky, everything else means regular dog, then kind of you have also this misgeneralization.
Yeah.
The rule you've learned is wrong.
Yeah.
Similar to like in the maze with the
right.
with the certain corner. So like my bigger question is like, what's conceptually different about the reinforcement learning case compared to the supervised learning case?
Yeah. So the question was what is conceptually different between goal misgeneralization and just misgeneralization for supervised learning or self-supervised learning. And they're very related to one another, so you shouldn't think of them as being like totally different phenomena. They are really similar. I think the difference is that in the case of reinforcement learning, these things are like much more complicated and sort of temporally extended. So it's not simply that it's learned some like weird trick for classifying a certain certain image class using features that we wouldn't want it to use. It's instead that it's sort of learned like an entire cognitive pattern internally that is leading it to pursue certain behaviors, right? So it's really the sort of complexity of the internal pattern and the fact that this pattern like persists over many different inputs, right? So over many different states, this pattern is all prevalent to influence those states. Yeah, but they're very similar. Yeah. Okay, so we're at the end of the section for goal misgeneralization, and I just want to go through core takeaways for this phenomenon, goal misgeneralization. So first of all, the most important one practically is that just because you've written down a reward function that accurately encodes what you want, so just because you've actually accurately specified what you want the agent to do, it does not mean that your agent will actually learn to pursue those goals, right? These are two different things, and you can have an agent which is trained with a perfectly specified reward function, but does very badly at pursuing the goals that you actually wanted to pursue when you move to a new environment. This is what matters practically. Two is just you should be aware of the phenomena. So when there's a distributional shift, you should expect this to happen or be wary of this happening. So be wary of distributional shifts, look out for them, and think about whether the training distribution actually matches the deployment distribution. And if it doesn't, you can think about ways in which your reward function may not encode the proper goal when restricted to the training distribution. So when you're only considering the training distribution, your reward function might not actually specify the goal that you want. The third, like other really important thing is that goal misgeneralization is interesting as a failure case because unlike other failure modes, it doesn't imply that the agent is doing badly or like is incompetent. So goal misgeneralization can get agents that are very competent, so are very skilled, know how to do certain things, are very good at controlling certain parts of their environment, but don't pursue the goal that you want them to. So goal misgeneralizations can very competently pursue a goal that you didn't want them to pursue. And lastly is the sort of high-level conceptual point of the role of reward in reinforcement learning is selection of cognitive patterns, not thing that the agent is going to maximize. The agent doesn't maximize the reward. It doesn't even see the reward. Rewards are used to select patterns within the agent. And this is the sort of correct way to think about how rewards operate in reinforcement learning. All right, any further questions before we move on from this portion of the lecture? Cool, okay. So now we're going to cover reward hacking, and we're going to cover two different situations in which you would expect to see reward hacking. So the first situation in which we might see reward hacking, sorry, I've got ahead of myself. So reward hacking generally occurs in goal misgeneralization the reward was correctly specified. There wasn't anything wrong with how we specified the reward. It was something about the distribution of the environments, the distribution of the training environment and of the testing environment, right? In contrast, reward hacking occurs when we're using a proxy reward. So when we're using a reward that is different from the one that we actually want the agent to maximize. So reward hacking occurs when we have a reward function that we're using to train our agent, so we're using as a selection mechanism, and it doesn't fully encode the goals or rewards that we actually care about. So there's something that we actually want the agent to do, and a reward function, in some sense, like doesn't specify everything about the good behavior that we want. And we're going to cover two different situations in which this might be true of our reward function. So if this is the case, then the reward function we're using is known as a proxy reward, because it's standing in for the reward that we'd actually like to use. Okay, we're going to go through like a formal definition of reward hacking to sort of unpack like what we mean when we talk about this. So we're considering the case where we have two different reward functions, r and r prime. And so we can think, if we like, about r prime being the proxy reward. So a true reward r that we actually want the agent to pursue, and some proxy reward r prime that we're going to train the agent with, right? And we can define the policy objectives, which we've seen throughout the course, which are just if I sample trajectories according to my policy, so policy pi, what's the cumulative reward that I'm going to obtain, right? And I'm going to define another policy objective for the proxy reward too. So I've got a policy objective for my true reward, a policy objective for my proxy reward. Now, reward hacking refers to a situation in which I have a policy that's doing very well according to my proxy reward, but does poorly according to my true reward. So in other words, I'm training using a proxy, and it's resulting in a policy that's doing very, very well according to the proxy, but poorly compared to the actual reward that I care about. So let's sort of see how we can flesh this out mathematically. So we say that these two rewards, r and its proxy r prime, are hackable over some policy set, so some set of available policies. So this could be all policies that can be represented by my neural network, for example. If there's a pair of policies such that my policy pi is doing better according. Sorry, I think this is slightly wrong. It should be that my my policy objective assigns a higher value to pi than it does to pi prime. So sorry, that prime should be inside the brackets over the pi there. So my policy objective assigns a higher sort of rating to my policy pi than the policy pi prime. But, and again, there should be a prime on that j. So my proxy reward assigns a higher value to the policy pi prime than it does to the policy pi. Yeah, sorry, I think I've like messed up the indices on this. It should be a j prime there instead, and it should be a j and a pi prime on top. Yeah. So essentially what this definition is saying is that I have my pair of reward functions are hackable if it's possible to do find a pair of policies where one of the reward functions assigns a higher value to one policy than the other, but the other reward function assigns a higher value to the opposite way around, right? So in other words, if my two policy objectives, j and j prime, disagree about the ordering of the policies, in this case, my policy, my proxy reward is hackable. Okay. Does anyone have questions about that? Sorry about the typos. All right. So let's see two situations in which I may want to use a proxy reward. So the first of these situations is shaping rewards. So often when we're training a reinforcement learning agent, the true reward that we care about is very sparse. So an example of this might be chess. When I'm training my RL agent through chess, the actual reward that I care about is whether it wins games. So I'm going to get a +1 if it wins the game, -1 if it loses, 0 if it draws, right? But this is a really sparse signal to learn from, meaning that that most of the transitions in the environment result in no reward. It's only for checkmates that I actually get any reward whatsoever, right? And so this makes it very hard to learn a good policy for this environment, because I essentially have this very, very sparse learning signal that I'm supposed to learn from. And in this case, we might use a proxy reward that contains more dense information about what good behavior looks like. So I might use a proxy reward that says, for example, that I'm going to give points to my RL agent whenever it captures pieces from the opponent, right? And give it a punishment, so a negative reward, whenever it loses pieces to the opponent. All right. Yep.
Would you apply the same naming to RHF, so the reward model that would be a proxy reward?
Yeah.
Technically speaking, the training data is not a reward model.
Yeah.
So you could being strict say, well.
Yeah. So the question was, would we still use this terminology for RLHF? I'll come on to RLHF in the case of reward models. I would treat it as a separate case of this. Yeah. Okay. So the more dense reward signal that we might use is called a shaping reward. So we're going to see now on for shaping rewards, reward hacking can occur when the agent develops a policy which obtains a good shaping reward, but does poorly according to the true reward that we actually care about. And in this case, we can think about it as the agent is exploiting the places where the true reward and the shaping reward, the proxy reward that we're using, come apart from one another. So this is sort of the classic example of shaping rewards leading to a poor policy. So this is a game called Coast Runners, and the agent was essentially trained. So what we wanted from the agent was that it goes around this racetrack and it completes the course in a very short amount of time. This is the thing we actually care about, that it can go around these tracks really, really fast. But the reward that we used was just the score that it obtained, because this is much more dense. You get scores for like picking up bonuses within the environment, overtaking, stuff like that, right? So there's a much more dense signal that we can use. And what we're going to see is that because it's a much more dense signal, because these things come apart, the reinforcement learning agent learns a sort of pathological policy which does really well at obtaining points, but really badly at the actual goal of going around the track. Let's see if this works. So this is the boat that the agent's controlling, and the sort of policy that it ends up pursuing is that it learns that there's this harbor here where there's a bunch of I think boost blocks that it can pick up, and it can do this sort of loop where it spins around and it keeps picking up these blocks because they keep respawning. And it's doing terribly at running doing well in the race, but it's accumulating a lot of points in the score, right? So it's doing really well according to the proxy reward, the shaping reward of like obtain points, or really poorly according to the reward of win races, right? So this is an example of a pathological policy where these two things have come apart and the agent has learned to exploit a situation where they come apart, leading to detrimental behavior according to the true reward. Any questions about this? Yep.
So just to make sure, the game is about finishing the course, I don't know, in a very short amount of time, but the reward model to select policies they've used is this point score. So every time you kind of get any kind of reward, according to this, you basically, like, these actions are weighted out.
Yeah. So yeah, because it's getting because there are rewards that whenever it picks up objects, because the score's going up, those actions get reinforced and that gets selected for. But it doesn't actually lead to the kinds of behavior that we want, because it's different from the true reward that we care about, which is just winning the race. Yeah.
So you may be about to cover this, but instead of in progress rewards, sometimes people use like self-play, right? Like where it's like Alpha Zero, where like if there's a very sparse reward signal, you just do a lot of it, and you just sort of generate that sort of artificially by making it play itself. Is there sort of analogous failures for reward hacking that come from self-play, or is that like a different?
It's a different thing, yeah. So self-play doesn't do anything to change the reward, and it's not really about. So self-play as a mechanism is not really about like dealing with sparse rewards.
Okay.
Yeah. Okay, great. So one situation is where which we've just covered, reward shaping, it's where we handcraft a reward to give sort of more information about what good behavior looks like, but the policy finds some pathological way where it can get very good reward according to the proxy, but bad according to the actual thing that we wanted, because we didn't realize that there's some place where these two things come apart, some place where the shaping rewards don't actually work. So another situation in which it's very, very common to use a proxy reward is reinforcement learning from human feedback. So there's lots of desirable behaviors where it can be just really difficult to write down a reward function for that behavior. And as sort of the most important example of this, we have language models, where when we're training a language model in a chat context, it can be really difficult to write down a reward function that encodes what it means to be polite, or what it means to be helpful, right? What it means to be harmless. So these are all things that we care about in our language model, but we can't write down a reward function that encodes these things, right? So you might think like politeness, like maybe you can just write a reward that like discourages swear words, but it's possible to be very impolite while not swearing at any point, right? And so it's really hard to write down something that encodes this. And what we're going to do instead is train a neural network that outputs rewards in accordance with our preferences. So we have this data set of preferences about what we prefer the agent to do, so the kinds of completions that we prefer our language model to generate, and we're going to use this to train a function that's supposed to output higher rewards to completions that are more preferred, right? And this is called reinforcement learning from human feedback, and what we get out of this is what we call a reward model, because it's a neural network that is standing in for our reward function. Yeah. Any questions about this? Cool. So because the reward model is a neural network, it can often be adversarially exploited. So it's possible to find examples where the reward model will output a really high reward for behaviors that you don't actually want. So behaviors that you aren't actually you don't actually want the system to display. And when we sort of push the reward model too hard, so we really heavily optimize for a high reward, we can get what we call reward model over-optimization, where we develop policies that actually do badly according to our preferences, because we've found the place where our reward model comes apart from the actual preferences that we have, because it's failed, that reward model has failed to generalize across the entire distribution. There's sort of adversarial examples for it, for example. Yeah, and this is sort of a paper that looks at this in the context of language models, where they consider two different methods for optimizing for reward. One is best event sampling. So you have your initial policy, and you just sample n completions from that initial policy and select the one with the highest reward. And the other is reinforcement learning, where you're training your policy starting from some initial policy that does okay, and you're training it to get higher and higher reward according to this reward model via an algorithm like PPO. And these show, let's unpack these graphs a little bit. So the dotted lines, the lines for different colors correspond to different reward model sizes. So how big is your reward model? We generally expect that bigger reward models will be more robust. So they'll do better. They'll actually encode more of the information that we want. And we have both a proxy and sort of the actual reward that we're trying to optimize. So the standard, the thick lines, the filled lines, are the actual rewards that we care about. and the dotted lines are our proxies. And we're going to optimize for the proxy and see what happens to our actual rewards. And we see that for both of these, it's more severe for RL than for, well, actually, the axes are very different, so let's not compare them. But for both of these, as I increase the sort of distance from the base policy, so that's what's on the x-axis here, distance from the base policy, my proxy, so these dotted lines are going up. So I'm getting higher rewards according to my proxy, which is what you expect, right? If you keep training your training, or you sample more completions and select the better one, you should get a higher and higher reward. So these proxies go up. But eventually, once I reach a certain point, the actual reward obtained by the policy starts to go down. So it's very severe for the reinforcement learning case that we see over here, where as I keep pushing, I get to a certain point where I sort of maximize the actual reward that I'm getting, and if I push further from that, I start getting a lower and lower reward. And eventually I go right back down to where I started, and if I keep pushing further than that, I'll actually become negative. I'll actually do worse than I would if I hadn't trained at all. Right? Does anyone have any questions about this?
Yeah, clarification question. So over-optimization in this case basically happens when proxy reward and the real reward are coming apart. But this is a different phenomena from overfitting. So we're not actually overfitting the proxy reward. We might model the proxy reward perfectly and also generalize this proxy reward perfectly from examples.
Yeah.
It's that we use two different reward models and they are coming apart if we go really far along the proxy reward. Yeah,
that's excellent. So completely correct. Reward model over-optimization is different from overfitting to the proxy. So it's not something where like, we haven't sampled enough from the proxy, and because of that, we haven't generalized properly. You can sample as much as you like from the proxy, but the issue is that the proxy is different from the actual thing that you do care about, from the actual thing that you really want to maximize. Yeah, does anyone have any final questions to close us out? Otherwise, we'll sort of end the lecture. Yeah. Wonderful. Thank you all very much for attending.